All right, so we said that inside two plates, if you have two plates of charge, which is like capacitor, which we are going to talk about next chapter, these are two capacitor plates. Usually they are very close to each other compared to their dimensions. So you can consider them as infinite plane of charges. And each one, remember we had a formula which was electric creates an electric field that is equal to sigma over 2 epsilon naught. But here, if you have two of them, in between, the electric fields add up and create each one sigma over 2 epsilon naught becomes sigma over epsilon naught. And outside, they cancel each other. So again, you see that this comes from the fact that we talked about if you have a surface of a conductor has a sigma charge on it, it creates sigma over epsilon naught at the surface of conductor. So in this case, these two ideas work together. And then we went to talk about a couple of examples. I'm not going to go over them again. And we got to this one, and I said that this is a problem. There are many problems like that, and they are explained in this video. If you click on the link later on when I put it up, you can click on it and watch the video. And if you have time today, I will come back to it. Here is the next question I want to discuss. You see here, we said it says that a charged particle is suspended at the center of two concentric spherical shells that are very thin and made of conducting material, non-conducting material. Figure A shows a cross section. Figure B gives the net flux phi through a Gaussian sphere centered on the particle as a function of radius r of the sphere. This is a typical sphere I drew here. It's a sphere, and that's a Gaussian sphere. These are real spheres, and they are made of non-conducting material with some charges, uniform charges on their surface. The scale of the vertical axis is set by phi s equals to 5 times 10 to the 5th Newton meter squared over Coulomb. So this Q, see, this is 5 from here to here. So each one of these vertical rectangle, each one is 1 times 10 to the 5th Newton meter squared per Coulomb. And it's asking, what is the charge of the central particle? What are the net charges of shell A and shell B? All right, so here it is plot of its flux through a Gaussian surface like this as a function of the radius of the Gaussian surface, which is the sphere. Okay, so this, in this case, the radius is less than radius of A, and this is the flux through that. Okay, and then when the radius becomes larger, passes the radius of shell A, suddenly drops to another value, and then when it becomes larger than B, then it jumps up again to this point, to this value. The question is, what is the charge of this particle here at the center? What is the charge of this shell A, and what is charge of shell B? All right, any ideas how to do part A, for example? What is the charge of the central particle? You see, the Gauss law says what? Says that the flux through any closed surface, especially this sphere, Gaussian sphere, is phi, which is integral of E dot dA over its surface, closed surface, is equal to the total charge inside divided by epsilon naught. This is Gauss law. So here, this flux, which is this integral, is given by this plot or graph. All right. So for example, for this sphere, if R is this, we are around here. The R is here. So this graph shows that the flux is this much. We know that each one of these is 10 to the fifth. So flux here is equal to 2 times 10 to the fifth Newton meter squared per Coulomb squared. And we know, according to Gauss law, is equal to the charge inside, Q enclosed, divided by epsilon naught. And what is the charge inside? The charge inside in this case is just the charge of this particle. Let's call it Q. So this is Q over epsilon naught. Therefore, from this equation, Q can be solved for. Q is epsilon naught times 2 times 10 to the fifth Newton meter square over Coulomb square. But epsilon naught is what? Epsilon naught is 8.85 times 10 to the negative 12 Coulomb square over Newton meter square. If you multiply that by 2 times 10 to the fifth Newton meter squared over Coulomb, you get Newton meter squared canceled. One of the Coulombs cancel. You get some Coulomb as Q. So Q is equal to 2 times 8.85, which is 7.7, right? 17, sorry. 17.7 times 10 to negative 12 times 10 to negative plus 5 times 10 to negative 7 Coulomb, which is how much? We can move this, becomes 1.77 times 10 to the negative 6 times 10 to the negative 6 Coulomb, or 1.77 microcoulomb. Okay.
Professor?
Yes.
I have a little, I was a bit lost on how you got 2 times 10 to the fifth. I know you got it from the graph, but
yes,
where exactly?
You see this phi s is given 5 times 10 to the fifth, and that is this much of the graph.
Mm-hmm.
That's 5 times 10 to the fifth. I said this is, at this point, is 2 times 10 to the fifth.
Right.
Right?
Yeah.
Does it make sense?
Yeah. I was just wondering if anything beyond that matters. Any of the graph beyond that.
All right.
Position.
You see, when the radius of the Gaussian surface, which is a sphere, the green sphere that I have, you see that with radius r, that is less than radius of the shell A.
Yeah.
If no matter how much that is the radius from 0 to this point, you see this jump is because of shell A.
Oh.
Before that, it is all less than radius of shell A. Basically, this is the radius of A at this point. This point is radius of B.
B. Yeah.
All right?
Yeah, that's perfect.
So Q, we found Q, charge of the central particle, 1.77 microcoulomb. All right? We just apply Gauss law, which says that flux of electric field is equal to, there's E also here, flux of electric field is equal to charge for any surface but then we apply it to this kind of surfaces for the spherical Gaussian surface. All right. And now if you have a Gaussian surface like that, so this is done. Now I'm making the circle larger. You see now? This is now R is this much. This is my Gaussian surface, the green one. Now R is between RA and RB, means that we are somewhere around here. How much is the flux? Flux is this much. So flux for that Gaussian surface, flux of the electric field is equal to negative 4 times 10 to the 5th, right? And then that should be equal to the total charge inside, Q enclosed, divided by epsilon naught. So Q enclosed in that is equal to epsilon naught times that, negative 8.85 times 10 to the 10 to the negative 12 times 4 times 10 to the 5th, right? And the unit will be Q. It will just be Coulomb. So now if you multiply that by 4, it becomes negative twice the other one, 1.77 times 2. It becomes how much? 1.7 becomes 3.4, 3.53, 3.54 times 10 to the negative 6 Coulomb. So Q enclosed in that is equal to negative total 3.54. Is that right? Microcoulomb. But that is what is the charge inside? There's a Q here and Q of the shell A also inside. So this is Q plus Q of A. And from there, we can find Q of shell A. Q of A is equal to negative 3.54 microcoulomb minus Q, which is 1.77 microcoulomb. If you add these two, what do you get? QA becomes 1, 7 and 5, 12, 3 and 5. I have 5.13 negative. Negative 5.31 microcoulomb. All right? So this is the charge of shell A. On the other hand, you could say that this drop is because of shell A. So you can say, you could say directly, the drop is how much? It's 6 times 10 to the negative plus 5 times epsilon naught, which is 8.85 times 10 to the, and of course negative 10 to negative 12 is the charge of the shell. If you do that, you get exactly the same, negative 5.31 microcoulomb. All right. So the drop, this drop is due to the charge of shell A, right? Because as you increase the radius of the shell, increase the radius of the Gaussian surface, it is constant as long as the radius of Gaussian surface is less than the shell A. As soon as it reaches shell A, passes shell A, then the charge of the shell A is inside. And the flux drops like that because of that. And then it remains the same as you see in here, remains the same until you get to radius of B. Right? And how much is the charge of shell B? See this going up, this jump is because of shell B. How much is this jump? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's phi due to B is equal to 10 times 10 to the 5th, and then multiply that by 8.85. No, this is that, and then Q of B becomes then 10 times 10 to the 5th times 8.85 times 10 to the negative 12 Coulomb. So becomes 10 to negative 4 times that becomes 8.85 positive times 10 to the negative, how much? Negative 8. Right? Should be negative 7. No, this becomes 10 to the 6. Becomes 10 to the 6. So it becomes 8.85 microcoulomb. That is Q of shell B. So you see, you can apply Gauss law to find the charges. Any questions? All right. The figure shows a cross section of a long, thin-walled metal tube of radius r equal to 3 centimeter with a charge per unit length of lambda equal to 2 times 10 to the negative 8 centimeter per, coulomb per meter. What is the magnitude of E at radial distance r equal to r over 2 and r equal to 2r? Graph E versus R for the range 0 to 2R. So I think you can answer the first one easily. What is the electric field at the radial distance R equal to R over 2? So this, it says thin means that we ignore this thickness. And if R is equal to R2, we can take a Gaussian surface like a cylinder like this, and with long cylinder like that, right? And then we said that because of symmetry, we have Gauss law, first of all, says that integral of E dot dA is equal to Q enclosed over epsilon naught for this Gaussian surface. So this is our Gaussian surface. And when you have that, then you say, okay, because of symmetry, E dot dA, E is the same everywhere on this cylinder, and it is radial. So E dot dA becomes E times the area of the cylinder, and is equal to Q enclosed. What is Q enclosed in that cylinder? How much charge is in that Gaussian surface that I draw? How much charge is in that? Do you see any charges in that cylinder? This Gaussian surface?
No.
The charges are all outside it. So that's 0. Because A is not 0, so E should be 0. Remember, we had shell theorem for cylinders. We said that inside a thin-walled cylinder, there's no electric field. And outside, it acts like a thin line of charge. Remember? That was the shell theorem for cylinders. So we should expect that. And that was from Gauss law, and we see that again. Now, if you are at a larger distance, larger radius, we can think about a cylinder like this, right? This is now Gaussian surface. Then we can do the same thing. This is integral of E dot dA is equal to Q enclosed over epsilon naught. And then we say because of symmetry, E and dA are in the same direction, and E is the same everywhere on the surface. So E times A, which is now, if the distance here is R, E times 2 pi R times L becomes, we did that before, but I'm just repeating. E times the area becomes the total charge inside, which is lambda times L. Lambda is the charge per unit length. If you multiply by length, becomes the charge inside divided by epsilon naught. And then you see that L cancels, and E becomes lambda over 2 pi epsilon naught R, which we can write 2k lambda over R, because 1 over 2 pi epsilon naught becomes 2k, right? And this means that outside this cylinder, the shell acts like a line of charge, which is again shell theorem for cylindrical shells. Outside the cylinder, acts like a line of charge, infinite line of charge. Okay, so that's not surprising. We did that before. So inside, the electric field is 0. Outside, we can use this formula. So E becomes 2 times 9 times 10 to the 9. Lambda is 2 times 10 to the negative 8 divided by R, which is R is now 2R, which is 3 centimeters. So 2 times 3 centimeter, 3 times 10 to the negative 2. Right? So these powers of 10 just gives you a 10 factor. One of the two's cancels, get 18 times 10, 180 Newton per Coulomb. Right? So the electric field at the distance of 2R becomes 180. And it says graph E versus R for the range R equal to 0 to 2R. If I want to graph, what does it look like for the shell? For the shell, if R, let me make some room. Sorry. All right, now get rid of all of this. I have fresh. All right. Now I want to graph. We said that if electric field versus R, if you want to graph it, if this is the radius of the thin cylinder, as long as you are inside in here, like say, as long as you are inside, the electric field is 0. So the electric field will be 0 in here all the way until here. So, and then suddenly jumps to a value at the surface and then goes by 1 over R. So this is at 2R. So at 2R, we found that to be 180. And we know that if you go R, it changes by inverse of R. So this goes at 360. And the graph will be 0 in here and suddenly jumps and goes to that part. So that would be the graph. All right, so this is the electric field versus R. Okay, does it make sense? Any questions? All right, so this is E is 0 here. Here E is equal to 2K lambda over R. All right, so let's go to the next one. Here is a similar situation, but we have an figure A shows a narrow charged solid cylinder that is coaxial with a larger charged cylindrical shell. So this is the narrow one, and this is the cylindrical shell. Both are non-conducting and thin and have uniform surface charge densities on their outer surfaces. Figure 2341b gives the radial component E of the electric field versus radial distance R from the common axis, and ES is 3 × 10⁻³ Newton per Coulomb. What is the shell's inner charge density? What is the shell's inner linear charge density? What do you think? If you are at this point, what does it mean? Just before this point, 3.5 centimeter, see this is the R in centimeter, this is the electric field. Just before 3.5 centimeter, the shell doesn't create any electric field. The electric field is just due to the thin, narrow charged cylinder is the middle one. You can call it wire. And this cylinder. So there's a wire and a cylinder. And just before that, in here, you are inside the cylindrical shell. It doesn't create any electric field. And then you see that this is K lambda, 2K lambda over R is because of the wire. This drop is due to cylinder. It's just before 3.5 centimeter, after 3.5 centimeter. So you can see that this drop, which is how much? ES is 3 times 10 to the third Newton per Coulomb. This drop is also the same. You see this drop, this is the ES. This drop is also the same. So the E field, E of the cylinder, is equal to 3 times 10 to the third Newton per Coulomb, right? And on the other hand, we know that just outside the cylinder, it acts like a linear charge, line of charge. So that is equal to 2k lambda of the cylinder divided by R. So that we want to find this lambda of cylinder. And R is at 3.5 centimeter, right? Because we are at 3.5 centimeter, suddenly before that and after that, it drops by that much. R. So lambda of the cylinder is equal to E of the cylinder times R divided by 2k. So it becomes 3 times 10 to the third times R, which is 3.5 times 10 to the negative 2 over 2k, which is 2 times 9 times 10 to the 9. Right? So you in the numerator you have 3 times, if you 10 to the third and 10 to the negative 2 cancel each other, it becomes 10. 3 times 35 is 70 divided by 18, and then you have 10 to the negative 9 Coulomb per meter. So it is 70 over 18. I don't know how much is that. That's about 3.89. So lambda of the cylinder is 3.89 times 10 to the negative 9 Coulomb per meter, or 3.89 nanocoulomb per meter. All right. Of course, if you take another point on the like at 3 centimeter, if you estimate how much the electric field is at this point, you can estimate the charge per unit length of the wire. But you see that at this point, charge per unit length of wire, the electric field of the wire is just this one of these steps here. The electric field of the cylinder is 3 times as much. So you can, if you divide this by 3, you get the electric field, you get the lambda of the wire if you want. You can calculate that, but the question is not asking for that. Any questions? I'm going to move on. Here is a small circular hole of radius r equal to 1.8 centimeter has been cut in the middle of an infinite flat non-conducting surface that has uniform charge density sigma 4.5 times pico, 4.5 pico means 10 to the negative 12 times 10 to the negative 12 Coulomb per meter squared. A z-axis with its origin at the hole center is perpendicular to the surface. In unit vector notation, what is the electric field at point P at z equal to 2.56 centimeter? And it gives you a hint. See equation 22.2. 0.26 and use superposition. This equation, in fact, should be the equation of a disk, equation of the electric field of a disk. E field of a disk. Remember, the electric field of a disk of radius r and with the surface charge density sigma was sigma over 2 epsilon naught, if you remember, times 1 minus, I guess it was z divided by z divided by square root of z squared plus r squared. If the radius of the disk is r and you are on the axis of the disk and at distance z from the center of the disk. Okay, this was the formula, and we can use superposition. What it means is that you can consider the electric field of this equal to this electric field is equal to E field of a plane, complete plane, minus E field of the disk. Right? And electric field of the plane will be sigma over 2 epsilon naught minus the electric field due to the disk, which is sigma over 2 epsilon naught times 1 minus z over square root of z squared plus r squared. Right? And if you add these two, this times 1 cancels the other one, and negative times negative become positive, becomes sigma over 2 epsilon naught times z over square root of z squared plus r squared. This is the electric field of this system now. Right? So now you have sigma, you have z, r, everything you can just plug in to find it. All right? You can continue but for yourself. Here, the figure short section in figure, short sections of two very long parallel lines of charge are shown, fixed in space, separated by L equal to 8 centimeter. Uniform linear charge densities are 0.6 mu microcoulomb per meter. I'm so distracted, sorry. For line 1 and -2 microcoulomb per meter for line 2, where along the x-axis is the net electric field from the two lines 0. This is the same as the problem I gave you on the quiz for today. And you have until midnight to finish it. But of course here, one is they are symmetrical around the y-axis, and in the other problem in the quiz is different. All right, so we have L equal to 8 centimeter, means this is 4 centimeters, 4 centimeter. And linear charge densities are plus 6 microcoulomb per meter, is plus 6 microcoulomb per meter. And the other one is minus -2 microcoulomb per meter. And we want to see where along the x-axis is the electric field 0. Okay. For a line of charge, we have a formula. Electric field that it creates equal to 2k lambda over r, where r is the distance to the line. All right. So let's say at this point they make electric fields that are 0. And each one, of course, this gives you the magnitude of the electric field. And we know that the direction is away from the line of charge, directly away if the lambda is positive, and toward if the line of charge is negative. So for this line and this first one creates an electric field at this point. Let's call it point P. And at this point, the electric field of 1 is this way. Let me call it E1. For 2, the electric field is toward it. So this is E2. So you see that they are in opposite direction. It is possible to find a point where the two are the same magnitude and they cancel each other. But if you look at this point, for example, this line 1 creates an electric field this way. Line 2 also creates an electric field that way. They cannot cancel out. If you look at this point, line 1 creates an electric field this way, away from it. Line 2 creates an electric field that's toward it. But you see the line 1 that has a larger lambda, but also is closer. So always E1 is greater than E2. So there's no way they can cancel each other. But here, because the larger one on the right side, the larger one, oh, did I?
Yeah, we lost it. Okay.
Yeah, okay. On the right-hand side, the larger lambda is also farther away. You see, the larger the lambda and the closer it is, the electric field is bigger, right? So if the larger one is farther away, it is possible for them to cancel out. But if the larger one closer, they're not going to cancel out. So let's set E1 magnitude equal to E2. And at point P, with x equal to x, it's at the coordinate x. All right. X not, I mean. All right, so what do we have? We have E1 equal to 2k lambda 1 divided by the distance of P to 1. What is the distance of P to 1? Because if this is x, you see, this is from the y-axis is x, but the distance from line 1 is x plus this distance. So can you see that it is x plus L over 2? And E2 is 2k lambda 2 divided by x minus L over 2. You see that? Oops. Yeah, from here to here is x. This is x plus L over 2, which is, we call it R1. And this distance is R2 from here to here, to line 2, as all R2 is x minus L over 2. So E1 is 2k lambda 1 over R1, E2 is 2k lambda 2 over R2. And we want these to be the same. So 2k lambda 1 over x plus L over 2 equal to 2k lambda 2 divided by x minus L over 2. And now we can solve for x. and 2k cancel out. And lambda 1 and lambda 2 are given. Of course, this you can put absolute values, because basically you see this equation, I wasn't very careful at the beginning. This gives you the magnitude of the electric field. So it should be magnitude, absolute value of lambda. So you can put the absolute values of lambda, 6 microcoulomb and 2 microcoulomb. So lambda 1 is 6 microcoulomb divided by x plus L over 2 is 4, equal to 2, not negative 2, because we put absolute value, 2 divided by x minus 4. And then we can cross multiply, get, and you can also cancel a 2. This becomes 3. 3 times x minus 4 becomes equal to x plus 4. Right? So it becomes, come here, 3x minus 12 equal to x plus 4. And you can move all the x's to one side, all the numbers to the other side. So 2x equals to 4 plus 12, 16. So x becomes 8 centimeter. Why is it centimeter? Because I put centimeter here, I get x in centimeters. If I put meters, I get in meters. And of course here, microcoulomb per meter and microcoulomb per meter, they cancel out. The units cancel out. All right. So we don't need to write them. As long as you put the same units, it's okay. So we find that at x equal to 8 centimeter, they have the same electric field. So that 8 centimeter means that this L is 8 centimeter, right? L was 8 centimeter, L over 2 was 4 centimeter. So it means the same distance you go over. Sorry, the same distance from the x. So if this is line 1, this is line 2, this from here you go the same distance. So at this time it means that 4 is here and 4 is here. Is the distance to the line 2, the distance to line 2 is 1/3 of the distance to line 1. And that makes sense because the line 2 has 1/3 of the charge, right? So that makes sense. This is just to make sense of it. All right. Any questions?
So 8 centimeters
Is the
past the origin?
yes, the position.
Okay. Yeah, position of point P, correct?
P.
Yeah.
P. Yes.
Thank you. So it's not, we're not adding x to L over 2, right? Or
No.
yeah, we're just from the
Yeah.
origin.
Remember this was x. Remember?
Yeah. Oh, I see. My bad. Thank you.
Yeah, I wrote according to this x. Now we found x.
Hmm.
So it means 4 centimeter to right of line 2. Right? 8 centimeter from the center.
Yeah.
All right. Any questions? Any more questions? Thank you for sharing your thoughts. All right, let's go to the next one. I want to get to. Here is a bit tricky. Let me see what we have. I think it's better to spend time on these two. Here we have sigma over epsilon naught, sigma over 2 epsilon naught for each one of these planes, infinite planes, sheets, large plastic sheets. All right. So electric field for each one is this. Now you need to figure out what the charge densities are. It's not very hard. You can do it for yourself. All right. This one is a little bit tricky. It's not really, but let's see what we have. A solid sphere of radius A, which is 2 centimeter, is concentric with a spherical conducting shell of inner radius B, which is 2A, and outer radius C, which is 2.4A. The sphere has a net uniform charge Q1, which is 5 femtocoulomb. Fc Q1 is equal to 5 F coulomb, means that 5 times 10 to the negative 15 coulomb. Nano is 10 to the negative 9. Pico is 10 to the negative 15. Femto, this is femtocoulomb. Which is 10 to the negative 15 coulomb. Okay. The shell has a net charge Q2 equal to negative Q1. You see, Q1 is here. This shell has negative Q1. Q2, which is negative Q1. What is the magnitude of the electric field at radial distances 0, A over 2, A, R equal to 1.5A, 2.3A, and 3.5A? What is the net charge on the inner and outer surface of the shell? All right. So we know shell theorem, right? Shell theorem says that the shell, no matter what charge it has, doesn't create any electric field inside. So we can forget about the shell as long as we are inside the shell. Means that as long as R is less than B, shell has an E equal to 0. No electric field. As let me say, has no E field because of shell theorem. All right, but so the electric field as for R less than B is due to the spherical solid sphere, okay, of radius A. And remember, for the solid sphere, the electric field is 0 at the center, and it changes linearly to the surface and then goes 1 over square of the distance. Okay. So if I find the electric field at the surface, then I know that that is at R equal to A. Then I know at R equal to A over 2 is half of that. As R equal to 0, it is 0. At R equal to 1.5 A, it is 1 over 1.5 square of what is on the surface. And what is at R equal to 2.3A? B is 2A. C is 2.4A. So 2.3A is about here. What is the electric field there?
Negative Q1.
No. It is a conducting shell. A spherical conducting shell of inner radius B, which is 2A, and outer radius C, which is 2.4A. So at this point, we are inside a conductor. What is the electric field inside a conductor? Zero. Remember, we said that inside a conductor, the electric field is 0. And because if it is not 0, electrons will move and adjust themselves until we get 0. All right. So that is the part 3.2.3a, means part E, right? For part A, we know from symmetry E is 0. For part B, we can find from part C. So at the surface, So let me say part B, E is equal to 1/2 of E of C. In part C, the surface of the conductor. Surface of not conductor, surface of the sphere. Solid sphere. So as long as we are outside, which is the same as on the surface, it acts like a point charge. So E becomes KQ over R squared, which is A squared. And so it is KQ1 over, let me write R squared here. In charge of it is Q1, and the radius of it is A, so A squared. So E becomes, E in part C, becomes this, 9 times 10 to the 9, the charge Q1, how much is that? 5. 5 times 10 to the negative 15, divide by A, which is 2 centimeter, 2 times 10 to the negative 2 squared. So that becomes 10 to negative 4, cancels 10 to negative 15, becomes 10 to negative 11, with the 9 becomes 10 to negative 2, 9 times 5 is
45.
45 divided by 4 becomes 10.14, right? 5/4. 45 divided by 4. No, becomes
11.
11.2, right? Times 10 to negative 2, and Newton per coulomb, or this becomes 0.112 Newton per coulomb. That's EC. And E in part B is half of EC because we know that it changes linear. And in part D, let me continue here. E in part D is EC over 1.5 squared, which is EC over 2.25. Because if you increase the radius by 1.5, the electric field reduces by 1.5 squared. Okay, you can find that too. And in part E, we said that it's 0. In part F, it's at 3.5A. Where is the 3.5A? It's just outside, like this point. How much is electric field there? So this is D and F. Electric field at that point, we said that if you have a spherical symmetry, all these spheres act like a point charge. All the charge goes to the center, and you can calculate the electric field like a point charge. How much charge is total here? We have Q1 and Q2. Q2 is negative Q1. What is the total charge? Is 0. So E is 0, EF is 0, since Q1 plus Q2 is 0. Or you can say, okay, I can get a Gaussian surface here, a spherical. The E times the area becomes total charge inside. How much is this charge inside? Nothing, because there's a Q1 and Q2 is negative Q1. So the total charge is 0, right? And then it's what is the net charge on inner and outer surface of the shell? What do you think?
Would inner be 5 femtocoulombs, and then the outer would be -5 femtocoulombs?
Why is the inner 5?
Because of
Q1 is +5. What did we say?
Oh, it's inside a conductor
Yeah.
or shell theorem, correct?
Yes, but we said Gauss law requires that whatever charge inside a cavity of a conductor, this outer shell is like a conductor with a cavity. The cavity is the sphere of radius b, right? So we said if we have some charge in the cavity, the opposite of that comes to the surface. What is the opposite of Q1?
Negative.
-5 femtocoulomb. So -5 comes to the inner surface. What goes on the outer surface?
Positive.
The balance goes on the outer.
Oh,
The balance of charge of the conductor. How much is the total charge of the conductor?
0.
The total charge of the conducting shell is not 0. It's Q2, which is -Q1. So the -Q1 comes here, which is -5, and then negative Q1, and the total charge is -Q1, so 0 outside.
on the outside.
You see?
Yeah. Oh, what about the Q1 for the inside?
Q1 is inside, and -Q1 comes to the inner surface of the shell, right?
Oh, so everything in radius b, we're not like considering, it's just the outer.
Yeah, if it has more charge, if it had more charges, then the rest of it would go to the outer surface. But it only has -Q1, so all of that goes to the inner surface.
Okay.
Right? If it had any other charge, the balance of it would go to the outer surface. If it had no charge, then it would be -Q1 on the inside, +Q1 on the outside.
Oh, so the Q1 from radius A and the negative Q1 cancels each other out.
That's
I
right.
see.
So if you have a Gaussian surface like this,
Yeah.
the electric field in here is 0 because it's inside the conductor. So the integral of E dot dA is 0 for this surface. Gauss law requires that it should be 0 charge, net charge inside that surface. So if Q1 is here, -Q1 should be
So
on the inner surface of the conductor. Remember, we said that.
yeah. So if Q2 was like -6, then our outer shell would be negative Q or -1.
If
Or -1
yeah,
femtocoulombs.
if Q2
Yeah, if it were
Q2 was -6
femto.
femtocoulomb, then -1 would come here.
Mhm.
-5 would come here,
Okay, cool.
right? That's if it's not the case now. So I'm going.
Yeah.
All right. Any questions? All right. So this is also a very good question. I encourage you to go solve that. That's a bit different because there's no charges here. There's charges only. This is a non-conducting a spherical shell. So charges are distributed on the volume in this area. This is Q0 here. All the charges on the spherical shell. Okay. Figure shows a spherical shell with uniform volume charge density rho. Inner radius 10 centimeter, outer radius 20 centimeter. What is the magnitude of the electric field at the following radial distances? So at r equal to 0, can you tell that?
It would be 0, right?
0, because it's of symmetry, there's no electric field. And r equal to a over 2 around here,
0, because it's
0.
non-conductor.
See, imagine a Gaussian surface, there's no charge in it, and there's symmetry. 1.5a. 1.5a is means here, around in this, on this radius, around here. So in here, you need to get a Gaussian surface, a spherical, and then apply Gauss law for part D. Okay, for part D, you need to do that. And for part E, at point r equal to b, you can, you see, you just outside, the whole thing acts like a charge particle. At 3b also here, the whole thing acts like a charge particle. The only part that is hard to do is this E, this D, which you need to get this Gaussian surface and said, okay, E times the area, which is 4 pi r squared, is equal to Q enclosed divided by epsilon naught. And then what is the Q enclosed in this case? You need to calculate that. And that is the only tricky part of this problem. The other parts are simple. You know, E is 0, 0, 0. And for E, it's just like a charge particle, charge particle. The only one that is not obvious is D. All right. I'll leave that for yourself. Go think about it, see how much of the charge is in there, and figure it out. If you have any questions, you can ask me later. By the way, after these 3 chapters, I'm going to give you a test. I'm going to send an announcement, give you a test on all these 3 chapters. It will be a take-home test, and I'll give you a couple of days to do it.
Cool, thank you. Will there be like a review session for it, or no?
If you have any questions, you can ask me next time or come to my office hour.
Cool, thank you.
No review session.
All good.
Will it be like a time test?
You said
No,
take
it
home.
is no, it's not a time test.
Oh, okay. Thank you, Professor.
Take home. Yeah.
Can you show number 26 again?
This 26.
Yeah.
This one.
Yeah. I just want to take a picture.
Okay.
Right. Thank you, Professor.
You're welcome.
Thank you, Professor. Have a nice day.
You too. If you have any questions,
Thanks, Professor.
I'll be here. If not, I'll see you next time.
Bye, Professor.
Yes, please. Let me stop the recording.